So we can look at the reactions of alcohols, as we already said. So we've got combustion, in which they are reacting with oxygen to produce carbon dioxide and water. Okay, and remember, this was a possible alternative fuel that we were going to use as a greener fuel because it was going to be sustainable and I was going to be able to regrow it. So it has a very similar reaction with oxygen combustion reactions to your hydrocarbons. Okay, and I can look at balancing that equation. Okay, and then I can look at balancing the equation. So because I've got an extra oxygen in the alcohol, I only need 3 lots of oxygen molecules to balance my equation. Okay, with the reaction of sodium, obviously sodium reacts with water and can deprotonate to form sodium hydroxide. Exactly the same principle is going to apply for the alcohol. So I'm going to have, for example, if I start off with propanol and react it with sodium, I'm going to make the alkoxide of the propanol, okay, and hydrogen. And obviously, I need to balance that equation again to be able to look at producing the correct balance symbol formula for the hydrogen. Okay, with PaCl5, I can react that with an alcohol to form a halogenoalkane and HCl. So I'm going to get steamy white fumes from that reaction. So obviously that reaction, remember, has to be done in the fume hood because hydrogen chloride gas that is given off is severely toxic. If I've got oxidation, it depends on the type of alcohol that I have. If it's a primary alcohol, I can oxidize it up by a reflux to get me the carboxylic acid. Okay, if it's a secondary alcohol, I can oxidize it up to get the ketone. And if it's a tertiary alcohol, I'm not going to get any reaction. So we can link this in to reflux, and we can see that if we have some potassium dichromate, in my round bottom flask, okay, that normally is orange. Once the reaction is complete, that goes green. Okay, so I know the reaction is complete, and I set up my round bottom flask. Set up my round bottom flask so that I've got my reflux condenser with water in on one side and water out on the other. So as soon as the alcohol evaporates, it condenses back down again as it hits the cold water in the water jacket. Okay, so we can get complete conversion of our alcohol. So our primary alcohol again would form a carboxylic acid, secondary alcohol would form a ketone, and tertiary alcohol would get no reaction. Okay, so in this part of the video, we're looking at the reaction of halogenoalkanes as the second part of 2.10. So we need to be able to name and draw what the halogenoalkanes look like, explain their reactivity, so in terms of primary, secondary and tertiary. Okay, look at the preparation, how we actually make halogenoalkanes, the reactions and their uses. Okay, so in naming them we use the IUPAC nomenclature. So in this case, for example, if I had this molecule that's 1, 2, 3 carbons, okay, so that would be 1 chloro, because it's on the 1 position, and it's 3 carbons long, so it would be propane. Okay, if I was to have an example of a secondary halogenoalkane, remember our rules from earlier on. If it's the carbon with the substituent on it has got 2 carbon chains, it's a secondary. If the carbon on the chain has 3 groups on it, it's tertiary. Okay, so for example, that one would be called 1, 2, because it's easier to number from this side. 1, 2, 3, 4, so it's butane. That one is 1, 2, 3. So it doesn't matter which side I go for. 1, 2, 3, chloro, 3 methyl, and the carbon chain is 1, 2, 3, 4, 5, pentane. Okay, well we can look at the reactivity. Obviously, we've got a delta plus and a delta minus in each of these cases. So that's going to be susceptible to some attack by a nucleophile. Obviously, due to steric hindrance, the nucleophile is going to be less able to attack there. Okay? It's going to be slightly able to attack there because there's less steric hindrance. It can come in from the backside. Okay, this side there is no steric hindrance, so the attack is going to be much easier. So the reactivity of primary halogenoalkanes is going to be much greater than the reactivity of secondary, which is going to be greater than the reactivity of tertiary. Okay, so tertiary is going to be the least reactive. And primary is going to be the most. Okay, in terms of the reactions, I can simplify this down to look at different types of reaction. Okay, so I can look at the reactions with aqueous potassium hydroxide, with alcoholic potassium hydroxide, and with ammonia. Okay, with aqueous potassium hydroxide, I get substitution reactions. So I'm replacing my Cl minus with OH. In alcoholic potassium hydroxide, I get elimination. So if I start off with my RCl, I make a double bonded compound. Okay, and in ammonia, I get substitution. So if I'm starting off with RCl and adding ammonia, I end up with an amine. Okay, and we can look at the uses of these molecules. Obviously, if you have substituted along the alkane chain with or halogens rather. Okay, these are not going to be able to burn. Obviously, if they do not burn, then they're going to be very useful as flame retardants. Okay, and finally, we're looking at the preparation. Okay, so we looked at this already, and that within the preparation, we could start off with an alcohol and add PCl5, and that's going to make my halogenoalkane. Okay, we can also use metal halides, okay, except when you're trying to make brominated compounds and iodo compounds.